Okay, let me repeat again. According what I asked, according what I get, the message I get from the department office and the government of Taiwan announced that you are free to take your mask off if you decide to want to. Okay, there is no obligation or duty to do that. That's the first thing. The second thing is there will be no class next Monday because I was asked by President to do the presentation on behalf of our school to get the grant of the next 5 years for the university, which is exactly next Monday. So in order to make it up, we are going to move the class next Monday to tomorrow night. Okay, 6:30 to 9. Okay, 6:30 to 9. So the class, let me repeat, there will be no class tomorrow, next Monday. And we're going to have a makeup class tomorrow night. I think it's here. Here, 6:30 to 9. Okay, please take your lunch, take your dinner. Then you come to this classroom. We're going to have a makeup class tomorrow night. Is that clear? Is that clear? Yes or no? Raise your hand if you understand what I'm saying. All right, good. Okay. All right, and you sent an email today. Okay, remind those students who are absent in today's class. Okay, so we are going to, that's it. Okay, come back around 10:25. Okay. All right, this is where we were 2 weeks ago because last Monday we have a national holiday because of the tragedy massacre about 70-something years ago. So this is where we were. 2 weeks ago, we talked about why the VLSI is so valuable. And besides you look into from the technical viewpoint, you also can look into from the financial side. And this is what we were before, okay? So this is the breakdown of the VLSI economies. So there are two important costs. The first one is so-called the fixed cost. Fixed cost, you can consider that it is the rent of the house, okay, or the utility bills, this kind of thing. So no matter you sell one chip or 1 million chip, fixed cost is always the same. And it is called non-recurring engineering cost, aka NRE. And basically it covers all the time that you spend, all the effort that you spend, and all the human resources you need. Okay, it's called the RD cost, manufacturing equipment, marketing and sales cost. Okay, infrastructure of the buildings, and even the storage, blah 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 blah, a lot of things. Okay, so it's a fixed cost. Let me repeat again. It doesn't matter whether you sell one chip or 1 million chip. Okay, the fixed cost it remains the same. But the second one is called the variable cost. Variable cost depends on the volume and the quality of the chip. Okay, so the variable chip can be considered this way. We're going to explain later. So the overall cost per IC can be defined as the variable cost per chip plus the fixed cost divided by how many chips you sell. It's a volume. Okay, so that's the cost per chip. So let me explain it. Why we need a big wafer, or bigger and the better. So this is a very complicated equation. Don't panic. I cannot remember it, so I'm not asking you to remember it. You got to remember one thing. Okay, the cost of a chip. Okay, based on three factors: cost of die, okay, cost of testing dies, and cost of packaging the final test. So the cost can be composed of three important factors: cost is die itself, testing, and packaging. And then after that, divided by field test yield, final test yield. Yield means what is the percent? Okay, what is the percent good of that chip? For example, yield 99%, that means 99 out of 100 is good. Okay, 50% means that half of the chip is bad. something like that. And then times dies per wafer, okay, the price per wafer. The cost of die is cost of wafer divided by dies per wafer times the yield. And we have two empirical formulas. Okay, please do not ask me where they're from, okay? They are directly copied from the textbook. It's based on my observation. These are just empirical formulas, okay? That is based on some measurement result. Anyway, we have several reference constants over here. For example, defect density, it could be 0.3 to 1.3. And the alpha factor is 4.0. So we plug in these numbers into those equations. And let me give you the following examples to show why the design is so important. So if you are a lousy designer, okay, and the area of the area of the chip is 1 centimeter square, and then the wafer that your company bought, the diameter is 30, and D0, okay, D0, 0.6. And the wafer, this is a very fair price. It's about the same price you bought the wafer from TSMC. It's $1,500 right? So if you divide it, plug in all the numbers, and you divide it, okay, you find out that cost per chip, per die, is almost $4. $4 is a lot, okay? $4 is a lot. If you are talking about a chip, this is a very expensive stuff, okay? And the major reason why it's so bad is that you have a very big chip. The design is lousy. So why IC design is so valuable? Right now, if you can shrink the die, your design down to 2.5 millimeter square, then that'll become totally different ball game, okay? You plug in the same all the numbers, you got how much? 0.15 US dollars. That's a very attractive number. That means that this chip you design, okay, delivered by a very capable designer, it will be very, very cost competitive on the market. Okay, 0.15, come on. Same performance, much lower chip, everybody loves it. And about how to fabricate a chip, well, this is something that you and I cannot afford, because every foundry plant costs you 2 to 3 billion US dollars. Recently, I and my brother's team, we are working on the a project in India. We are not talking about the foundry to fabricate chip. We're just doing the testing the packaging. It costs like 1 billion. 1 billion for 3 factories. That's for very low end. So for this kind of high-tech plants, 2 to 3 billion is a reasonable price. So how big the size is about this, a city block, and it needs 100 people to work together so that this factory can function normally. So, and the most profitable period, okay, for that factory is that at the beginning, the stage, which is about 1.5 years to 2 years. And these are the normal price, okay, for different process NRE. For very old stuff, for example, 0.35, which is relatively out of date, okay, about 50K. And for the advanced stuff, right now you are using over here in this course, you are asked to do the design using 0.18. There now it could be 200K US dollars, right? And this is a fixed price, no matter how much chip you sell. And the wafer price, okay, depends on the size. For those 8 inches, I think it's around 1,000. For those 12 inches, it could be over 1,600, maybe up to 2,000. It depends on which foundry you talk about. So this is a price or the other costs you need to do the chip design. Okay, that's something that we talked about 2 weeks ago. And for the challenges, a lot of people ask about these things, even those Filipinos and Indians, they ask me, where are ahead of us in this field? Because I've been working and struggling in this field for over 30 years. So the challenges of IC design in the future is about a lot of things. Number one, interconnection. Interconnection means wires. Wires. Okay, for advanced devices, you very soon you'll be fully aware that all the wires become bigger than those transistors. Because you can shrink the size of transistor, but it's so hard to shrink, okay, narrow down the wires. It's highly impossible, okay? So in this case, the wire delay, the delay on the wires will be much, much longer than the delay created by the transistor itself, okay? So the game plan shall be adjusted to minimize the speed. Otherwise, you're going to have a very lousy design because you're going to pay a lot of price in terms of time on those connections. Okay, it becomes extremely slow. And even if you improve the speed of a transistor, it's not going to help. And the second thing is I consider the most important is the power. Power is a fundamental of everything. Without the power, we cannot sit in this room. Without the power, we cannot turn on the lights. Without the power, you cannot drive your cars and motorcycles to go anywhere you like. That's impossible. So power is an important thing because, unfortunately, the resources on this planet is so limited, particularly the power. Okay, the only unlimited power that we have is the solar from the sun. But the downside is that we have a very poor conversion rate, even if we use a solar panel. Right now, the conversion rate is around 15% to 20%. And you got to use a lot of space to harvest the power from the sun. You see a lot of panels on the field, on the roof, this kind of thing. So basically, that's the only unlimited power we have, as from the sun, from the Apollo. Besides that, everything else on this planet is limited. Even if you use a fossil oil, gas, okay, it's all limited. So, and due to the crisis of climate weather shift, we have been paying attention to the emission of carbon dioxide because that will cause the effect of a greenhouse, okay, and AKA global warming, and that will melt down all the icebergs on the north poles or south poles and cause the elevation of the seawater goes higher and higher and cause a lot of problems. Okay, we are going to have run into a very catastrophe weather disasters. Okay, so power is important thing. I'm going to show a lot of examples of power. And believe it or not, IC, okay, chip, or you call digital computation, costs a lot of power. Okay, I don't prepare that for today, but I'm telling you that's very true. Particularly, okay, when one thing shows up, which is artificial intelligence. Have you ever heard of ChatGPT? ChatGPT, okay? I believe some of you have already abused that kind of software to write your homework or composition. But the thing is, you don't know how much power that kind of AI equipment needs. Okay, perhaps I give you this story before. In 2016, there was a chess game between a South Korea Czech player and AlphaGo. Okay, well, AlphaGo won the game, no surprise. But what surprises us is that AlphaGo, in that game, AlphaGo cost us 30K US dollars for a single game to consume electricity bill. But the South Korean chess player only consumed $30 for the lunch. 30K versus $30. Think about it. Okay, now you can picture how much power you need to drive the AI. And this is not acceptable unless we have more energy efficient community devices in the future. Okay, number three is that we have a lot of constructive constraint, okay, on the market, because we are people. We are always selfish. We always like what? Something cheaper but faster. Okay, something more affordable but powerful. Okay, we like to have a very cheap, very not expensive mobile phone, but we like to have everything on the mobile phone. Technically speaking, these two requirements, they are against each other. So the low cost versus high performance, that is, we consider this as conflicting constraints, okay, on the markets. That's why we need a lot of IC designers to help. And as I said about AI, the system complexity getting bigger and tougher. So we need a lot of approaches to help. Okay, the most well-known one is called divide and conquer. We divide a big problem into several small problems and fix them one by one, and we group them together. All right, so we are going to have a problem to do that. And just besides the testing, we also have a problem to, besides the designing, we also have a problem to testing it. Okay, even though that we divide a big problem into several and many small problems, and we test everything is good, okay, but we find out there is something bad happen if we integrate them together and run the system. Okay, it always happens. You are going to run into this kind of problem as well. So for example, you design an 8-bit adder, okay, and then at the beginning, you and your teammates design a 1-bit adder, which worked just fine. Then after that, okay, then you say we copied 8 times and integrated these 8 1-bit adders together to come up with an 8-bit at the adder. But suddenly you find out it doesn't work. That's what I say here. Even though the subsystem works just fine, but when you integrate all the subsystems together, you find out there is some problem popping up, okay, after that integration. And then you will be panicked. Damn, okay, I have done everything I could in the subsystem stage. How come it does not work as I think? Yes, Tom Hanks say one thing every day. Okay, say one thing. That is very impressive. He said that shit happens every day during coding, but it is very true, particularly in the IC design. Okay, so the future perspective. So for the future, in this course, we ask students to do the low-level design, but okay, but it is doable in a single semester. But however, when you go to a real IC design house or go to the real company, you're going to find out you will never be asked again to do this kind of a trivial design. You will be asked to do a lot of system-level design. So, for example, in this kind of company, you already have so-called the excuse me, a process IP. And this is a kind of process IP, is a programmable SOC, was a SOPC kind of design. You already have something there. But what you will be asked is, okay, you got to add some features or add some extra functions, okay, using those existing IPs. Okay, this is called the system-based design, all right? And the second one will be cell-based design. Cell-based design will be taught in another course in this school, not in this one, because we are going to focus on the full custom design. For the cell-based design, you will be asked to write code. I know a lot of EE students, they really hate to do the coding, but the thing is, even if you don't like it, you have to do it, okay? Coding is one of the skills you should learn in the school because you need it. You need it. For example, C programming, C++ programming, SPICE, okay? SPICE, and then Verilog. Verilog is another one that you should learn in the school. You will regret, okay, if you don't learn it and you find a job in the market. Because in the real company, no one will spend their precious time to teach a rookie to do the coding because they assume you learn it when you were in school, right? They also assume you learn your electronics at school. They don't have waste their energy and resource to teach you again. So it's better for you to get prepared before you go over there. And for the full custom design, there are several topics very popular: memory, CPU or FPGA or other special purpose chips. And this part is right now is really focused on two things: AI and the power. And the power, okay, power IC. Because as I said, the limitation of energy give us a lot of problems. So there are a lot of terms that you should learn. The first one is called the IP, and AKA it is called the intellectual property. It's a pre-designed and a well-tested component. Basically, you have to pay for that to get either the source code of a design, or you pay for the schematic and the layout of that design. Okay, and on the market there are several companies working on special IP. So they are considered as IP providers or vendors. And hard IP means that you pay the money, you got the accurate block size, all the pin counts, performance, and the power consumption. It's very sophisticated. It's well tested before. All you need is just take it, plug in your design, and make all the connections you need. And then soft IP is totally different. You got nothing about the schematic. However, you got a code. This code can be written using the Verilog or VHDL. Okay, Verilog right now is the standard for industry usage. VHDL, okay, of course, it is welcome. But the thing is, VHDL is specialized for US military usage. Okay, so if you don't want to spend your time, I think at least you got to understand how to write a Verilog code. And in the middle is called a hardwire IP. Hardwire IP means that, okay, you know the block size, performance, and the power consumption, but you don't have the detail. And this kind of a hard IP, okay, will be applied on FPGA only. Okay, either Xilinx chips, Xilinx FPGA, or Atera. So for those IC designers in the design house, IP design house, sorry, it's either design the hard IP or soft IP. Okay, it's rare to deliver so-called hardwire IP. There's another term called the ASIC. And if you go to the Human Resources Bank, you're going to find out this term. It's called the ASIC. ASIC stands for application specific. I see. ASIC. Okay, it's really to understand that it is specially designed for special usage. Okay, special. For example, you have a system, a freezer, and this freezer has a totally different protocol from others. And then, of course, you got to control the freezer. So you go to the system house will go to IT design house to say, hey, do me a favor. I need a special IC for my freezer usage. So this kind of fully custom made is called the ASIC. So that the entire flow is almost the same as a full custom design. See, the product requirements, behavior description. Okay, because the system designer, they have no idea how to design IC. All they need is, okay, we want certain function, this and that. Okay, and I will give you, a sheet of paper describing all the functions we need. Then your team take it over to do the coding. Do the coding over here. Okay, do the coding over here. Then use the synthesize tool to synthesize into a gate level code. And then in the meantime, every step you move down, you got to do the comparison to check whether this is exactly what the customer needs. Right? If it's good, then we go ahead and move on. Then after the double comparisons, we can go to the physical synthesis and then check it again. Okay, not only we check the functionality, after the synthesis, we got to check the timing and the power. If it is also good, then the job is done. We tape out the chip for our customers. And then the next step will be up to the marketing guys to talk about how much a price and how much volume we like to deliver every month, every year. So this is the ASIC design. And these are just examples. You don't have to remember. You cannot do it alone. It's impossible, okay? This is IBM, very old stuff. It's called a PowerPC. Very old stuff. You just look at the blocks that you see. Very complicated. It's impossible for any guy to do it alone. You need our help. That's why a lot of IP providers are needed on the market. They give their IP, and then they got their pay. For example, I'll give you some example. Any IC needs an interconnect connection, right? So you got to need a block to take care of the Ethernet connection, and that's an IP. You got to go to the IP provider and pay for it, okay? And then take the either the software code, variable code, or take the hard IP plug into your design. Every system needs memory, right? So you got a cache. Cache is a SRAM. Instruction cache, data cache, and you got to design the size. Blah, 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 everything. This is all the blocks you need. Okay? So this is the functional block of a PowerPC. This design is older than every one of you. Okay? I think it's about 20 years ago. You check here. I2C, UART, GPIO, every block you see is a special design, is a subsystem design. And in this course, you are not going to design everything. So all you need is just take care, okay, one little block in the middle, and then you're good, because you are only the college kids. Okay, and this is the beginning stage of your career. So this is what you need to learn in this course. And for those buses and arbiters, they're too complicated. It's impossible. So basically, all you need to do is come up with either a SRAM design or a DRAM design, and that's it. All right, or some certain block, function block in the CPU. That's all you need. This is just one example. Okay, this is a second example. This is a camera. This is also very old. It's out of market. It's a Samsung digital camera, okay? For the camera, you got to have a blocks to deal with those lens. It's a CCD camera, okay? And you need the SDRAM card so that all the photos that you take or the customer take can be written into that SD card, okay? And then they can take out the SD card, go to the Photoshop, print it out, okay, to share with their friends or family, this kind of thing, right? Okay, the IRD, ERDA is the infrared, okay, it's a remote control. As you can see here, we have a lot of interfaces like ADDA, DMA controller, DM, and we got to have a JPEG and MPEG. MPEG is a video player, right? JPEG is for the photo display usage. So a lot of blocks. And on the upper right corner, you see that some of the camera is asked to be able to hook with a digital TV so that they can directly see all the pictures on the television. So you need a lot of interfaces over there so that this final product can be very competitive on the market. Otherwise, no consumers will buy it. Well, this is the second example. I think we have a number 3. Okay, this is the PowerPC is so big. Okay, it's very big. We have a lot of IPGA fabrics, hardwire, multipliers, this kind of thing. And the PowerPC, the one that we describe, is the one only standing here, and the rest are the auxiliary circuits. Okay. So In this course, of course, we only talk about digital designs. So as I said, there are many ways to design a digital system. However, we only have one semester and you are just beginners. So this is the overall possibility to do this implementation. And FPGA, I assume you learned it when you are a sophomore. You do the lab. You know how to use it. Use PLD, FPGA, CPLD. Basically, in our department, we use the FPGA. And then using the, I think it's Xilinx. And for certain courses, microprocessors or microcontroller, you use a platform. And then you do the assembly coding or C coding. This is the second approach. They are not covered in this course. It is assumed that you learned it already. In this course, we do the ASIC design, but we only focus on the full custom. Okay, if you want to learn the Verilog and the cell base, you go to other professors' course, which will cover the Verilog coding and the synthesis. So we are here. This is one of the ways, one of the approaches to realize a digital system. Okay, this is a very big family, and we are sitting here. That's all. Okay, so I'm going to skip these parts because they're just terms. Okay, microprocessor unit, DSP, digital signal processing. And PLD has 3 different types. Okay, PRA, PAL, ROM. 3 types. And FPGA, which you already know it, all right? And we're here for a custom. We are the lowest of the lowest. We are lowest of the lowest. Okay, we are all the way in the bottom. Because in this course, you are asked to do the detailed design. Very, very basic design. Okay, they deal with semiconductors, transistors, okay, schematic design. But don't feel bad, because right now, what you are doing is to increase your value. Because a lot of jobs, their entry level is very high. And if you know how to do the schematic design, layout design, you have more weapons in your hand when you go to the job market. Okay, trust me, those guys, of course, they understand the coding. But the coding is a very common thing. But for some students who really like to take the full custom design, they know a lot more. And that will increase your value on the market, okay? All right, so a lot of trade-offs we have to make. And I think this is the last one. This is a real product, an MP3 player. Right now, MP3 is gone because MP3 is wiped out by your phones. Okay, no one uses that. No young man uses that already. Okay, it's gone. So this is a very old stuff. It's a real 8000 MP3 player. It's a very simple one. See, this is so simple. And because it is simple, it can be designed and fabricated and sent to market very fast. All they need, okay, is a DSP processors and a codec, 2 chips. Why I'm showing this? Because on the job, on the market, okay, not only we compete, not only they compete, okay, which price is lower. They also compete which company can deliver the product faster. So I always joke about one thing, okay? You can consider the IC design is just like a race, Olympic race, 100-meter hurdle. Okay, only the top 3 got the medals, right? Gold medal, silver, and the bronze. Okay, nobody remembered number 4 and the rest. Okay, it is similar on the IC competition. Okay, the first one on the market very likely will have the lion's share of the market, 50%, 60%. Number 2 got another 20, 30%. Number 3 perhaps like a 10%. Okay, barely survive. And number 4, unless you have a very attractive price, very, very low. Otherwise, you have no chance at all. You have no chance at all. So this is one of the reasons why a lot of IC designers or the foundry engineers, they have to work day and night, okay? Because what? They are competing not just the power, also the speed on the market, how fast it is on the market. So basically, the semiconductor jobs, the pay is high, but you gotta pay the price as well. Okay, the price is that you're gonna sacrifice a lot, okay? It could be the worst case is you sacrifice your health because you have to work around the clock at some time. That's one thing. The second thing is that you're going to sacrifice the time with your family. You will sacrifice the time with your many girlfriends or boyfriends, okay? But you got to make your judgment or your decision whether this trade-off is worth it or not, okay? Life is simple. Life is simple. You make decision, you don't look around. All right, so this is the wrap-up of the first talk. Okay, and then we move on to the second lecture. Now we are going to our hardcore technical stuff. Now this is the first design that we are going to introduce you. It's called a ratio-less logic design. Ratio means that, okay, well, you and I, we have something in common, and we like to make a comparison. For example, my age is 60 and you're 20, so the ratio of our ages is 3:1. It's a ratio design. Ratio-less means that the design does not consider the size ratio of transistors. That means it is a robust design, robust. But however, since we don't consider the size, then the area or the cost of area could be a problem. But as I say, this is only the beginner's course, so it doesn't matter. Okay, first thing, the priority on your list is that you have to make it work. Okay, because your government, your school is going to pay for the money of the chip. So this is a ratio design. You have the luxury to abuse the areas. So let's start from the bottom, the hard rock bottom. Okay, switches. Before we go to the transistors, we go to the switches first, okay? Then if we do understand what the switch is about, then we explain what the switch logic is. And then based on that, we can go to a very systematic design way to, to design some basic gates. And what is a switch? Because as we said, there is no ideal switch on the silicon. We got to understand that all the switches that we know are realized by transistors. We have two types of transistor, N-type or P-type. Now, right now, I use the N-type to explain what the switch is and how it is realized and what is the good thing about that, or what is non-ideal features of this one. So NMOS goes first, then PMOS. Now, briefly, it is a symmetrical one. Then we have a TG. TG stands for transmission gate. Okay, the transmission gate is a composition of the previous two switches. Then, if we understand the TG switches, then we can go to design some basic logic, which is the gate. The gates that you learn when you are a freshman. Okay, so this is a switch. All right, so far we have treated the transistors as ideal switches. But the thing is, the cruel fact is they are not ideal. Too bad. All right, so these are the symbols that we use. Okay, these two, they are the same thing. They are N-transistor symbols. But the only difference is this is 3-terminal, and this is a 4-terminal. We have an extra one over here. That stands for the current from what? The current from the bottom, from the bulk. So if you don't like it, that's fine, okay? Because all the N-transistor, the bulk should be connected to the ground. Okay, it should be connected to the ground. So in most of the cases, you can remove that, and other guys will never misunderstand what you're talking about. But this is basically, this is a symbol used in the textbook in our drawings. But however, in those software tools, for example, Virtuoso you use in this semester, okay, in the Virtuoso, all the N transistor has to be drawn as 4 terminals. Is that clear? Okay? So 3 terminal symbol, okay, is only good for discussion. Okay, it's only good for representation in textbook on the papers. But for the real design in Virtuoso, you got to use 4 terminals. Okay, don't forget to do the connection, okay, with the first terminal to the ground. Okay, similarly, this is PMOS devices, PMOS transistors. The only difference is that we use a small circle at the gate to stand for the PMOS. And then the current direction is opposite to that of N transistor. It goes to the bulk. So this bulk here must be coupled to VDD, aka the highest voltage node of the system. All right? So this is the symbol that we use. So don't get confused. So, and then an on transistor that, okay, on means that, okay, it is good, or it is driven to turn on, so that, as you see here, if you ignore this part, we take this example, it's just like a faucet. Okay, faucet, this is like a pipe. Okay, right now, you open the faucet and the water will go through. So the water, okay, the current is, you can consider current is like the water in your house. So this is a faucet. You turn it on and the water goes through. All right? So that means the transistor is on. But as, sorry, the width of the wires, okay, is limited, just like the size of the pipes in your house is limited. So the current amount is just like the water volume in your house is limited by the size. So the on transistor only pass a fixed amount of current. So it depends on what? It depends on the terminal voltage. Okay, the voltage drops between these two. It is like the water drops between the pipes in your house. The higher the water pressure, the faster the water. So the current depends on the terminal voltages here. So based on this observation, we can derive the IV curve of that transistor. And you're going to use that, okay, throughout the semester and throughout your career in IC design. And the third thing is that transistor gate, source, and drain. Okay, we know that this is the faucet. It is called the gate over here. And these 2 terminals, one of them is called the drain, the other one is called the source. So how do we make a distinguish? Because they all look similar. So basically, in order to find out which is source, which is drain, well, for the N transistor, this is gate. Okay, this is gate. And in order to make sure that people understand the direction of the current, we use the arrowhead over here, okay, connected to the lower voltage part. Then we understand the current will go from the top to the bottom, and this is called the drain, and this will be the source. That's it. It's easy to understand. Otherwise, you can never tell which way the current will go. All right. So from time to time, you will see that on these 2 branches, you will see an arrowhead. If you see that, that means okay, they demand the direction of the current must be correct. If you don't see the arrowhead in the symbol, that means okay, both way, I mean, from up to bottom, bottom to up are acceptable. So this is the way to define the drain and the source. Is that clear? All right, basically. And for the P devices, okay, for the P devices, it's slightly different. Okay, the direction is different. Goes this way. This is for the P devices. The arrowhead also shows you the directions, okay, for the P devices, the P transistors. Okay, and how big is the current? The current is defined by C, which stands for the capacitance, how big that is, how big your pipe is. And this is a delta V over delta T. Okay, that is the amount. In a fixed period of time, what is the voltage change over there? So this is, and then we move the delta T to the left-hand side of the equal sign and move the I over here. You are going to see something that you really like. Okay, delta T means time. Okay, you want it faster? Delta T must be smaller, right? You want it faster? Everybody likes the faster stuff, a faster car, fancy car, okay, faster computer. So this got to be small. So based on this equation, how can we make it smaller, faster? We cannot have a big C. Okay, C must be small as well. So the devices, all the stuffs must go smaller. So the smaller, the faster. Okay, on top of that, want something fast, we got to have a big current. When I goes up, delta T goes down. So these are the important observations that we have. When we like the high-speed stuff, we got to make it small. Okay, we got to use a big current. So fast means big current. Big current means what? Big power. So the faster the CPU, okay, the more power it consumes. So that is why the desktop PC, some of the desktop PC has a fan. It needs a fan to cool it down because it's fast. That means not only is it smaller, but also means that it has a high power. And the high power creates the heat. If you don't remove the heat, that will kill your CPU, and your desktop PC will become a junk. Okay, so the capacitance and the current determine the power, determine the speed. This is a basic guideline. All right, so first thing first, let's estimate how big the capacitance is. So this is a very interesting observation, all right? So before we go to the 3 terminal devices, right now we only consider 2 terminals, P and N. It's really easy. So let me draw a picture over here so you understand why we are using this. So this is a cross section. So we already introduced you excuse me, the structure of the transistors. So this is what we have. This is the zinc oxide. This is the polysilicon, and this is gate. Okay, it's over here. Okay, so here we have N plus. That means we have abundant, a lot of extra electrons carriers over here. And this is a bulk. It's a P bulk over here. Okay. Before we use these 2 terminals, let's go to find out what happened here if we increase the voltage at the gate. Okay, it's just like a picture over here. So where there is nothing, okay, there is nothing. V0 smaller than 0 or equal to 0 is nothing. So here you see a lot of, because this is P, right? So you see a lot of holes here, just like over there. Just over there, right? And this is insulator, so nothing happened. Right now, okay, it's called accumulation mode. Nothing happened. Okay, even if you add different voltage on both sides, nothing will happen over here. Okay, it's closed. Then what we do? Okay, we gradually, okay, smoothly increase the voltage on the gate. So what's going to happen? What's going to happen is that when the voltage here goes up, it goes up because this is positive. Okay, this is positive, and it will attract a lot of, roaming electrons from here, from the bulk, go to this place. Go to this place. Then the combination of electrons and electron holes, then we create, a neutral zone, which is called a depletion region. There is nothing. Because all the holes here will be neutralized by these electrons induced by the positive voltage on the gate. Understood? Right? It's very easy. So then we got nothing over here. It's neutralized. It's neutralized. We have you can consider that all the holes are pushed back. Okay, or all the holes here are neutralized. And then this is a voltage. Okay, this is smaller than a VT, which is called a threshold voltage. So we have a threshold voltage over here. So when the V gate is smaller than V threshold voltage, but larger than 0, this is what's going to happen. We have a depletion region, neutral zone over there. Okay, right now we increase the voltage of the gate even higher. Then even higher, that when it's higher enough, we have a lot of electrons attracted by this positive voltage. So very soon we are going to have a very thin electron layers, in this channel, just increase it. Then this is what's going to happen. Over here, see that? This is called the inversion layer, inversion region. Okay, and the neutral zone, depletion region, will be pushed down. So right now we have electrons standing and sitting in this channel, waiting for the signal. What signal? The signal means the voltage drops between these two terminals. So now you understand how the transistor works. In the vertical, you got to have a very strong voltage to attract the carriers from the bulk to the channel. Then you add voltage drops on the two terminal horizontally. Then you can push the electron to move. The next one is that, right now we have a single layer of electrons over there. That's good enough. Then what we do something very interesting. What is that? Right now we call this one is a drain, and this is a source. Okay? Right now, if we directly make the drain, VD, large, positive. And this one goes to couple to the ground. What's going to happen? These are electrons, right? They will be attracted by the positive voltage. So the electrons will move to the right. This is the direction of electrons. So as you understand, the direction of a current and electrons are opposite. So when electrons move this way, that means current goes that way. Understood? Because the definition of the current is the opposite direction of the electron moves. So this one, the electron will go this way, but the current, I go this way. So that is why I said that when this one is grounded, this is source, and this is drain. When the voltage is high, this is high, and we gotta have a current go this way. Is that clear? Very simple, okay? No magic. It's just a simple, straightforward, basic semiconductor physics. Okay, let me repeat again. You add a vertical direction voltage to induce the carriers into the channel. Then you add voltage drops on both sides. You can push the current, okay, to move horizontally. So that is how the switch works. If the current shows up, that means the transistor is turned on. It's turned on. It is turned on to work. It is turned on to to do the mission, to do the job. All right? So this is just a simple explanation. Then we go to the equations. You understand what's going on. So after I explain on the board, and right now you can easily understand what the textbook said over here. So you see that we have a VG over there, we have a VD over there, we have a VS over there. See, this is that. And the voltage drop between these two terminals is called a VDS. And then the voltage drop of VGS is defined the voltage of the gate and the source, and the last one is the gate to drain. Gate to drain. Okay? So VGS equal to VG minus VS, VG is this way, and VDS equal to this. Okay? That's a three-terminal relationship. It's so easily to be remembered. The source and drain are symmetric diffusion terminals. And there's a diffusion terminal over there, right? So source is terminated as a lower voltage, as I draw over there. So remember, for the N devices, for the N transistors, the source, the voltage source goes to the bottom, goes to the ground, the lowest one. And for the P devices, it is totally opposite. The source of a P devices goes to the top, goes to the power supply VDD. So in this way, the VDS will be positive to push the current around. And the body is grounded, so the source is grounded as well. So there are three regions of operations. Okay, so in order not to make you confused, so let's go back to the first one, the previous one. So for the two terminal devices, there are three modes: accumulation, depletion, inversion. That's for two terminals, P and N. If we're talking about a real transistor, we have three modes as well, but they are not called that way. They are called the cutoff, linear, and saturation. I assume you learned this when you were a sophomore because it should be taught in microelectronics course, okay? If you forget that, go back to your textbook. Cutoff means that the VG equal to 0 or lower, so there's nothing, okay? There is zero carriers in the channel. Linear means that we have a small amount of carrier, which is electrons over there, okay, in that region. And what does the saturation mean? Saturation means that even if you applied a very large vertical voltage, okay, there is a limitation of electrons amount that you can induce, okay? So it's a two top. The most you can get from the size over here. So the current is saturated. You can never be higher than that. It's impossible. So it's saturated. So this is three regions. So this is a cutoff region. It's got nothing, okay? Because right now VG is coupled to the ground. It's got nothing, all right? You got nothing over here. See? It's prettier than I draw. You see that? It's blocked. This is electrons. There is nobody no electrons in the channel, nothing can be moved, okay? So IDS is almost nothing, zip. And then, okay, linear region as we increase the vertical voltage so that we have a channel, just like I draw over there, okay? And then the current flows from D to S, okay, because the electrons move the other way. And in this case, okay, the IDS will be increased with VDS because the amount of the current is small, but the voltage drops on both sides. The speed, okay, will be dominated by the voltage drop on this side. So the magnitude of IDS current will be increased with the increase of VDS. And in this case, the function of this one looks like what? Looks like a resistor. Looks like a resistor, okay? In the last case, because no matter how hard you try, okay, you increase the voltage in the vertical direction, you increase the vertical, the voltage drop in the horizontal direction, okay, the channel pinches off because you reach the maximum speed that the current can flow. You already drive the gate to attract the maximum number you can get, the maximum number of electrons you can get from the body, and that's it. This is the best you can get. That's all. So it is called the pinch off. So the IDS will be irrelevant to the VDS, no matter how big the voltage drop you drive. That's it. So the current is saturated. In this kind of mode, okay, the transistor acted like a current source because the amount is fixed. Okay, this is very important, the concept. So in the linear mode, the transistor behaves like a resistor. When it enters the saturation mode, it acts like a source, a current source. And it is very helpful for you to design many other ICs, for example, analog and power ICs, okay? Okay, so we are going to really calculate how much current we can have. So right now we go to the linear region first. So current depends on two factors: how much charge we have, okay? How fast they move. That's two things, okay? What is the amount of the electrons, or how much the charges, how fast they move. So now this is a pretty diagram for you to understand. This is the bird view of the devices. This is a channel device. Okay, remember that. This is where the current flows. Okay, the electron travels. Okay, from this side over there, the current goes this way. So this is the length. All right, and this is in this direction. This is the width. How big? Okay, the transistor is. So this is the width. The length and the width. Remember these two terms. Okay, and this is a side view over here. This is a side view. So this is gate, source, and drain. And this is the VDS over here. And this is the middle of the channel. The middle of the channel. So if this is this middle of the channel, so we can consider this is a half because this is VDS drop. This is a half of VDS at this point. So let's estimate, how much charge we have. Then we go to estimate the speed. So what do we have? Okay, we calculated the charge. Charge depends on the size. So the first thing is that how big the capacitance is. Okay, so the capacitance is equal to the CG over here. CG equal to, this is a permeative. This is a parameter, okay, of this material. And it is about 3.9 relatively to the free space. Well, I'm lazy. I always ask a student to remember it is equal to 4. It's easier, okay? Permeative is the permeative is a constant, okay, for any material. For the silicon oxide is 3.9. And this is a size, right? Because the capacitance is this is a conductor, this is conductor. So this is the area over thickness of the silicon oxide. So this is a constant. And then we take this one and this one together to come up with a C oxide. That means the standard unit parameter to calculate the capacitance for transistor. So anyway, just remember it is proportional to the size of the gate. Okay, W times L, width times length. Okay, this is a C. Now the next thing is, if we understand what a C is, then we can estimate what the charge is. So the charge is a C times V, right? Capacitance times V. And the next thing is that what a V is. Okay, what a V is. Okay, so this is what a V is. Oops, it doesn't work. Okay, over here. This is a VGC gateway channel. Gateway channel in the vertical direction. The voltage drops between this conductor and this conductor. And VGC equal to the VGS gate source subtract the middle in the center of the channel, half of the VDS, minus VT. VT is the minimum requirement, is over here. Minimum requirement to turn on that channel. Okay, you got to be higher than that, so you got to take this one away. So VT is the threshold voltage. It is a minimum voltage to turn on that device. Okay, somebody calls it a VTH, it's the same thing. Okay, it's the same thing. So based on these equations, then we can estimate how much charge we have. Okay, then the next thing is how fast those electrons move, right? Carrier moves. So charging for the end device, I'll say, is carried by electrons. Electrons are driven by the lateral horizontal electric field between the source and the drain in this horizontal direction, lateral. And E stands for the field. It's VDS divided by L. Okay, this is a basic microwave equation. Okay, V over L. And the speed, the velocity, okay, is proportional to the E. Okay, and this one is something that I can remember. This is the mobility of that carrier. Mobility of electrons times E over here. All right? So and what is a T? T is the inverse of V, L divided by V, right? Then divided by velocity, we can get the time for the electron to move from one side to the other. Then we get this equation. Okay, so this is the current, overall amount of Q divided by T. Then we plug in all the numbers we got. We get this important equation for you to remember. All right, this is the equation for the linear region. So based on those estimations, we got IDS is the amount of the charge divided by the time that we have, and plug in all the numbers, all the parameters we have, we got this equation. And this equation is meaningful, okay? Beta is over here. Okay, beta is over here. Beta is the size information. This is the mobility of the carrier. This is the size. And this is the unit capacitance. And VGS, the gate voltage versus the source. Subtract V threshold, subtract half of the VDS. So in this case, we do understand the current, okay, in the linear mode is related to the VDS over here. Okay, it's related to the VDS. Of course, it is related to the size. This is question you got to remember, okay? But this is for the linear region. Right now, if we push it hard enough to drive the, you use a higher vertical voltage and a higher lateral voltage. So when the VDS is higher, okay, higher than VGS, VDS is higher, very big, okay? Push the velocity to the limit, and finally it's pinch off. Then the drain voltage no longer increases the current. So what you're going to get? You're going to get this equation. All right? Now this is what you got to remember. If the transistor is forced to be saturated, you got this equation. IDS equal to, beta is the same. No, nothing changed. But look at it here. It's VGS subtract VT squared. The VDS, this term is gone. No longer there. So when it is saturated, the current is highly predictable because all we need is to know what the VT is, threshold voltage, and what the VG we have. Okay, of course we know the size. So that is why in digital design, 99.9% all the transistors are driven into saturation region. You want it to be saturated, so it's easier to predict what the behavior will be. All right? So 99%, you like to drive the transistor into saturation because the current is predictable, okay, and you know what it's like. Okay, you know what the VG is, and you know the size. Then you know the drill. Okay, you won't be panicked. If you go back to check the linear equation, it's slightly more complicated because you got to worry about what the VDS is, right? You got to worry about the lateral horizontal voltage drop. Sorry, it's a little bit out of time. So this is saturation. Okay, well, we're going to take a break. This is the summary of these three modes. You got to remember this one. The cutoff, you got nothing of ID. The linear is over here, and the saturation, you follow the square rule, and you got no problem in estimation. Okay, let's take a 10 to 15 minutes break. I'm going to get a cup of coffee. Okay, go to toilet room.